Okay, still people are joining, so let's just wait another 2 or 3 minutes before we start today's lecture. And for the questions today, just like yesterday, try to use the campus wire so that even if after the lectures or the lab sessions, the course assistants and I will be able to stay and then trying to answer your questions as much as I can. And the link, you can find it, to check here. So you can go to this one, this chat room, and then try to, yep, I just copied and pasted the link on the Zoom group chat. Let me put it on the campus wire as well. It doesn't, hold on, let me just try it again. So then what you can do is you can go there and then go, I'll just copy and paste it. So you have to be logged in first. So you have to log in to the campus wire and then click the link. Let's see. So what you, yeah, for some of you, link is working. If not, what you can do is you go to the campus wire. There's a chat rooms button on the left panel. And then, so maybe I can actually show you. So you will go to, let's say, campus wire. And then once you go there, you're going to go to the natural language processing. So our AMI page, right? You probably can see it already. And then you click the chat rooms. And then there are a bunch of chat rooms on the middle panel. And then today we're going to use the lecture machine translation to ask questions. And then we already see that some of the people started to write message here. So Manuel said hello. So this is where the question should be asked. So is everyone fine with finding the chat room? All right. Good. That's very good. Let me just see. Where is it? All right. Okay. Perfect. So today we are going to have our lecture first, and then you're going to have a break, after which Yashua Bengio is going to join remotely for you to have a question answering session. And then after Yashua's QA session, we're going to come back and then start talking about our own, let's say, the lectures. So stay tuned. So now I think it's about time we should start. We have more than 50 people already joining. So what we are going to learn today first is to talk about what are some of the textbooks that you can use. So these textbooks are very, very useful, in the future if you want to learn more about the natural language processing, especially with the focus on using deep learning. And not even that, but also if you want to later go on as to work for, let's say, software engineering companies or even in the PhD programs, you need to have these foundations. And then if you have these textbooks, you can always go back into the textbook and then trying to see what were the missing pieces that you didn't know, right? So that's why it's important to look at the textbooks whenever you need. So one of the highly recommended textbooks or the latest textbooks that I can recommend you is the Introduction to Natural Language Processing by Jacob Eisenstein, who used to be a professor at the Georgia Tech in Atlanta, but now is a research scientist or the senior research scientist at Google Brain. So he wrote this book during the past 2 years. This book was just published last year. And then you can even find the draft PDF available at the URL marked in the slide. So I highly recommend you to go to this link and then trying to see what kind of, let's say, other materials there are that you should know in natural language processing. And especially if you're interested more on the, okay, you want to know how to implement all these stuffs. So we are learning that through the lab sessions this week, but of course, these lab sessions during this 1 week is just not enough. Then what you want to do is you want to get this book by titled Natural Language Processing with PyTorch, Build Intelligent Language Applications Using Deep Learning by the author, the Lip Lau and the Ryan McMahon. And then that was published also just last year. And then this book is unfortunately not free, nor the PDF is available, but this book is pretty thin and then you may be able to afford to buy it. Highly recommend it. They actually show you using PyTorch how to build all these language models, dialogue models, text classifiers, and so on. So it's going to be a good book to have. And then the third one, this is more on the academic side, is the Neural Network Methods for Natural Language Processing by Yoav Goldberg, who is a professor in Bar-Ilan University. And then this book is slightly older than the other two books. It was published in 2017, but it's relatively thin, only 300 pages long. And then there is a freely available version that is the journal paper that is available from online from the Journal of Artificial Intelligence Research. So I highly recommend you to check out these 3 books. And if you could afford, please do try to buy one of them. Or you can also recommend Ames to purchase 1 or 2 of these books. All right, so today we are going to start talking about machine translation, but before talking about machine translation, we need to talk a bit more about the recurrent network first. So the recurrent language model is the language model technique that we talked about last in the yesterday's lecture. That is, this is a language model that allows us to build or go beyond the n-gram language model or the Markovian property we had to impose. And the recurrent language model works by recursively enumerating or the recursively accumulating the information that is being streamed in. That is, when we have a sequence of words or there is a sentence or paragraph, you can think of this as a stream of data arriving. So I'm receiving the first word, the, and then the second word, and then the third word, and then the fourth word, and then this can just continue on and on and on. And then the idea of language model or the autoregressive language model that we have learned is to trying to predict what is going to come next in this stream of words. So given the, what should be the next word? Given the cat, what should be the next word? Given the cat is, what should be the next word? And then once we know how to compute them, that is the probabilities of the next tokens, all we need to do is multiply all of them or sum the log of all of them in order to get the probability of the entire stream or the sentence or the log probability of that, right? And then how language model does is to recursively apply these 3 procedures: read, update, and predict. So what do I mean by that? So read procedure corresponds to, here's a new word coming that has arrived. Let's try to read that one. And then, and then update corresponds to, so now that I have read this, I need to update my own memory state or the hidden state. And then once the hidden state is updated, we can now predict what the next word should be. And then prediction is done by trying to predict the categorical distribution over the all possible next tokens, right? And then we do that again and again. So read, update, and predict. Read, update, and predict. So what it means is that we can think about building a recurrent neural network or the recurrent language model as having two components. First component is the transition function that performs both read and update. And then read is done because the input is going to be the previous word. So this corresponds to read. And then the update is done because it takes as input the previous state. This is used for the update. And then the input is going to be one-hot vector, right? So 1, 2, or any one of the tokens that has been received. And then the previous state is going to be just the hidden state from the previous time step. And then once these are inputted, first what we do is we do the embedding. So now here's the new word arrived. What is the embedding of this new word? And then that is going to be used to update the hidden state that is based on the previous state. So here's the previous state, right? And then what we do is we're going to simply take the weight linear combination of the input and the previous state with a bias and then apply the nonlinearity in order to get the new hidden state. So this transition performs both read and update, right? So here's a read and update. And then we end up with a new hidden state after this. Now, often when building a transition function, the most naive way is to build a simple feed-forward layer. And then feed-forward layer corresponds to having a linear transformation of the inputs. And the linear transformation of the previous state is as usual. So we have the previous state, we multiply that with the weight matrix. But in the case of the input, because input is going to be one-hot vector, right? One-hot vector or the integer in this, those two are the equivalent thing. We're going to have an embedding. So we call it embedding or table lookup. Once we do the linear transformation of these two inputs, that is the actual input, that is the word that has just arrived, and the previous state, what we need to do is we need to apply the element-wise nonlinear transformation. Without any nonlinear transformation, this network is not going to do anything interesting, right? So for now, we're going to call this specific recurrent activation function or the transition function a naive transition function. We're going to go into a more complicated one at some point, and then we're going to stick to using hyperbolic tangent function. Now, once we have updated our hidden state, what we need is to predict, right? So that was the step here. That is, given the hidden state, now predict it. That is trying to compute the categorical distribution over all possible next tokens. And then for this, we're going to define something called readout function. Now, given the updated hidden state, so this is going to be updated hidden state, now trying to get me the distribution over all possible next tokens. So input is the current state. And then now what we have is a readout weight matrix and bias vectors. And then as you can see from this readout weight matrix, the input to this is going to be a d-dimensional hidden vector, while the output is going to be as large as the size of the vocabulary. And then there was a question yesterday about this projection layer. And in the lab session, we looked at number of the projection layers. So this readout function effectively is projection layer from the yesterday's lab session. And then once we do the projection, so which is this part, we need to now apply the softmax function, which we learned yesterday. Softmax function is going to turn a real values into the corresponding probabilities. And then the probability, those probabilities can be used for us to either generate the next token or score the next token. Once we know how to score the next token as the probabilities, we can get the actual probability of the entire sequence or the sentence, right? Now let's look at it once more. So we have the input, the current state, and then we're going to perform the linear combination. And then this linear combination has a very interesting aspect, that is, we're trying to compute the compatibility between a trainable word vector and the hidden state. What do I mean by the compatibility? Compatibility comes from computing the dot product. When we have two vectors, if they are well aligned, when they are pointing into the same direction, this dot product is going to be really, really high. And then if this dot product is really, really high, the probability of the next word being W is going to be high as well. However, if these vectors are not really well aligned or pointing into the opposite direction, this dot product is going to be very, very small, leading to a very, very small probability. That's why we meant by the compatibility. And then of course, this compatibility is going to be turned into the probability by the softmax normalization. That consists of two stages. First stage is exponentiation, second stage is the normalization. Now this leads to the predict stage. Now, once we have this kind of recurrent network, we can compute the log probability of a training sequence quite readily. As we read one word at a time, we're going to read, update, and predict. And then whatever the log probability of the next token is going to be used in order to compute the log probability of the entire sequence. And then because we have a training set that consists of all these sentences without any annotation, so that's the difference between the text classification and language modeling. Language modeling is still unsupervised learning, and in particular in this case is a self-supervised learning because the sentence itself provides natural target, right? So because of this, it's a self-supervised learning. And then all we need to do is we try to minimize this negative log probability or the average negative log probability as we talked about over and over yesterday. Now here, we're going to quickly talk about what it means to do the stochastic gradient descent. So the stochastic gradient descent is the optimizer that we're going to use over and over with this kind of sequence data. So one interesting aspect of the sequence data is that every single data point is unique in a sense that the length differs from one example to another. If I build a mini batch with 4 sentences, those 4 sentences may have different length from each other, just like what you're seeing there. And then what are we supposed to do? Because what we want is that we want to have as regular shaped tensor as possible in order to maximally benefit from the GPU's parallel computation. So the first thing we can do is simply to do the padding and masking. And then this is what you learned in the lab session yesterday. So you're going to simply pad them, so pad the short sentences so that all the sentences in each mini batch look like they have the same length. And then what you're going to do is you're going to remove any kind of computation from this padded region using the mask. So that makes sense, and then that's what we are doing generally with the NVIDIA GPUs. However, that's not necessarily the best way to go because it's going to be a bit wasteful. So the slightly smarter way to do that is to try to ensure that the length differences are minimal. And how can you do that? You're going to sort all the sentences according to their length and then build the mini batches sequentially so that the differences within mini batches, the length differences in mini batches are going to be minimal. So if you compare this one and then this one, you do see that the size of the padded or the number of the padded tokens or the padding token is minimal in the second case. So that can help. However, this does introduce a bit of bias because you are not sampling the examples in each mini batch uniformly and independently from all the other mini batches, right? Why is that? Because as soon as I select, let's say sentence 1 or sentence 4, I am now looking for the sentences of the similar length only, rather than looking at all the other sentences when I try to choose a sentence 3 and 2. However, in general, because we have a large enough data, it turned out to be reasonably okay. Now, we can be even smarter if we want to go into a much more details or the lower level, let's say details. is trying to process one word at a time. Now, when we process one word at a time, we can process all of these all together across the mini batch. But when we arrive at some point, we are going to remove the first sentence that was the shortest one. And then we are going to process the remaining ones. And then we arrive at the end of the second shortest one, we're going to remove it. And then we're going to process these words simultaneously for these two sentences. But once we arrive at the end of the sentence 3, that is shorter than the sentence 4, we're going to remove it from the computation. And the rest of them, we're going to process it sequentially only for one sentence. And this actually saves us a lot of the wasted computation. So these were the wasted computation in this smarter padding, but now we don't have any waste of computation. However, this requires you to do a lot of, let's say, extra computation or the conditional branching that may not necessarily be faster in practice. So once we know about all these, let's say, details, now we need to think about doing the backward computation. As we talked about, backward computation is one of the most important things that we need to do in order to compute the gradient of the loss function. Now we're going to consider having a single sentence. So when we are given a single sentence, we know how to compute this loss function because that's just a forward pass. And then once that is done, we need to compute the gradient. As we talked about yesterday, everything is automated largely these days using PyTorch, TensorFlow, or whatnot. However, it is important to know about what goes on inside in order to know better about what can be improved. And the recurrent net provides a very interesting opportunity there because recurrent neural net is in some sense the deep, very, very deep neural network because the depth of the network grows as the length of the sequence grows. So it can easily be the deepest or the deepest network anyone has ever built. And then the insights that we get from this kind of recurrent network applies to any very, very deep feed-forward network that you can think of. Now, first thing we want to do is that we can rewrite this per sample cost into a per step cost function. That is, because our loss function was a sum of all these low probabilities, low conditional probabilities of the next token, the gradient of that is also going to be sum of the gradient of the low probability of the next token with respect to the parameters theta here. It's just because the gradient or any kind of differentiation is a linear operator that we can push this gradient operator inside this summation. And then what it means is that we just should look at the per step cost function and then trying to see what kind of gradient of the per step cost function with respect to the parameters we get, and then we simply sum them across the time steps. So let's look at the per step cost function. Now, in order to compute this per step cost function, which was computed here, right? So this is where the per step cost function is computed. We need to backpropagate through in multiple steps. So first, we need to compute the cost derivative. That is, given the input to this log p of xt, given x, all the previous tokens, now given this quantity, what is the derivative of this quantity with respect to the input to the softmax, or the softmax linear transformation followed by softmax. And then that is going to be the output of G here. And then once we compute that, what I need to compute is that, okay, what is the gradient of, or the Jacobian of G with respect to the input to that? So we have the readout function there, so we can now compute the gradient of with respect to that. And then now I can compute the gradient of the cost or the per step cost function with respect to the hidden state. And then that is going to be simply to multiply whatever I have computed with the Jacobian of the G with respect to HT plus, so this is the important part, plus this temporal gradient. That is, we have the two arrows going up, right? So let's try to write it a bit more carefully here. I'm going to erase this. So if we look here, let's see. Let me try to zoom in. Oops. Okay. So if we look here, starting from the current hidden state, there were two arrows going out. One is going out for read, that is to predict, and then the other one was going out in order to update the next state. So there were two of these points, meaning that when we do the backpropagation, we need to consider both paths. And then those both paths comes in this place. That is, in order to compute the gradient with respect to this current hidden state, what we need are the two things. One is the gradient of the per step cost function here, and also we need to now sum the temporal gradient. That is the gradient of all the future per step cost functions with respect to this hidden state that is computed. Yes. So this is what we want to compute. So there is something wrong here. So this is not there. I'm sorry about that. This should be all the future things. T prime goes from t plus 1 to t gradient of the log of p t prime, oops, x t prime, given all those before, times the ht plus 1. Oops, I'm sorry. Yeah, I'm sorry, I don't really use the PowerPoint for this kind of thing, and then this is not really easy to use. Oh, oops. I'm not even sure what I am here. Okay. But yes, okay, I'm going to just do this. Sorry about that. Times the, why has the color changed? Okay, I'm sorry. This is always confusing. What is going on here? Oops. It's just not working as I want it to. But I'm going to just release the fixed version of the slide later. I think that's going to be easier. I think something's wrong with my pen here. Let me just try to close it and then restart it. Okay. So here, what we need to do is, instead of this, what we need is the gradient of the, let me see, sum of t prime going from t plus 1 to large T log p x t prime given all the previous one with respect to h t plus 1. So then I can multiply that with the ht, the Jacobian of the ht plus 1 with respect to ht, and then that's going to be the signal coming in from the future effectively. And then once I compute the gradient with respect to ht, I can now compute the gradient of this per step cost function with respect to the parameters r as well as u and b as well as w. And then once I do that, I can now go back in time, try to accumulate these gradients, right? Because it was all the sum. So let's think about, so this was the mathematical notations, but let's think about more intuition here. So how do we actually know, or what does the backpropagation through time compute? What this backpropagation computes is that trying to measure the influence of changing the parameters or the input just little, and then on the actual output or the loss in the future. So had I changed or perturbed the parameters or the hidden state at any time point, how will that perturbation influence the future cost functions? And then that is precisely what I need to know, because if I know how it's going to influence it, then I'm going to perturb or change the parameters in a way that is going to maximize or minimize the future cost function. And because it's cost function, we often want to minimize. So that is, as you see on the slide, if I perturb the hidden state time step t, what happens to this per step cost function at time step t plus n? So what I'm trying to measure is the influence of the past, in this case t, on the future, that is t plus n. And then in order to measure that, what we do is we're going to start from the ht. Oops, I'm sorry, this shouldn't be there. We're going to look at the ht, how the change in the ht influence ht plus 1, and then I'm going to continue checking that kind of influence over time and multiply them over and over. And then eventually I'm going to arrive at ht plus n. So how does my change in ht influence ht plus n? And then how does that change in the ht plus n influence via this readout function, the output or the loss function at the time step t plus n? So, and then this actually allows us to measure this kind of long-term dependencies or the influence. So before we continue, let's just answer one quick question by the Mbaya Babu. So why did we compute the gradient of R with respect to HT in? So we did not compute the gradient of R, gradient of the loss function with respect to R, right? So R is here. R is a parameter in a readout function, right? So what it means is that if we want to compute the gradient of the per step loss function, that is this one, with respect to R, and then this does not involve HT at all. So yeah, we never computed that. So, okay, so this is the intuitive version of the backpropagation through time. And then, you know, like this is the animation I made, right? So let's just look at it once more. So I'm going to change something. So this should be HT, I'm sorry. So I'm going to change something at the time step t, and then I'm going to measure how things are changing over time so that eventually I know how the change in HT resulted in change in the per step cost function n step later, right? And then we are not assuming anything bidirectional. This is the autoregressive recurrent language model. So we only move forward in time. Now, of course, forward or backward, it doesn't really matter because you can always flip the order of the words in the sentence. However, in this case, we're going to say we're going to go from left to right in forward only. There's nothing bidirectional here. So, and then once I know how to measure this influence, so again, this shouldn't be here, my bad, I'm going to fix it later. Then what it means is that I know how to change my parameters so as to maximize the low probability of the correct next token. So when we look at this intuitive picture of the backpropagation through time, we realize that there is something weird going on. And that weirdness comes from the fact that we need to compute all this with temporal Jacobian or derivative. So what do I mean by the temporal derivative is that when the time step goes from one step to another, we need to know what the change in the hidden state at time step t is going to have as an influence on how it influences the next time step's hidden state. And then we need to multiply this temporal derivative or the one-step temporal derivatives over and over in order to measure how the change in the time step t is going to influence many steps in the future, n steps in the future. But then what ends up doing is that with the naive transition function, the temporal derivative looks like this. This is a diagonal of the derivative of the hyperbolic tangents. That's the derivative of the nonlinear function with respect to the input to the hidden state at time step t, multiplied by this transition matrix. So I'm going to call it transition matrix. Transition matrix here. So this is the gradient. So this whole term, this one term within this product is the gradient of the f of ht minus 1, xt minus 1 with respect to ht minus 1. So this is the temporal gradient, right? And then we're going to multiply this over and over, so n many times, in order to compute how much influence the change in the hidden state at time step t we have on the loss function after n time steps. And then according to Yashua Bengio's paper from 1994, this is problematic. Why is it problematic? It's because we're multiplying the same matrix over and over. If you remember, or let's just do a very simple mental, let's try to see like what we can get. Let's say I have a single number, and this number is slightly larger than 1. Then if you multiply this number over and over, what happens? This number is going to easily increase. And then this is the idea of the exponential growth, right? And then what it means is that after just multiplying this number, however small that was, that is just slightly larger than 1 over and over, is going to explode. And then the same thing or a similar thing happens with the matrix as well. If you multiply the matrix, square matrix over and over, then the norm of this diagonal entries will explode if the largest eigenvalue is larger than certain value, and then often is larger than 1. And then the similar thing happens the other way around. If you think about having one number, one scalar that is slightly smaller than 1, and then if you multiply it over and over, what happens? It's going to exponentially converge to 1. It's going to converge to 1 very, very rapidly. And then that happens again with a matrix. If you multiply the square matrix over and over, and if the largest eigenvalue is smaller than 1, it's very likely that the diagonal entries of this matrix is going to vanish towards 0 very rapidly. And then this whole thing, the norm of this whole temporal gradients, or the influence of the change in the hidden state and time t on the future, vanishes or explodes very quickly. And then these are the problems of the so-called vanishing or exploding gradient that was identified by the Yashua Bengio in 1994 and also was further analyzed by Razvan Pascanu and others in 2013. Now, in the case of the exploding gradient, it turned out that it's not even a problem, in fact. That is, we can actually let the norm of the gradient explode, but then we're going to simply clip the gradient. So on the right side of this plot, we actually do see a very nice illustration of what exploding gradient is. So when the learning algorithm stays in this basin or this flat region on the right side, the gradient, norm of the gradient does not explode. But when it gets really, really closer to this kind of, let's say, cliff here, then there is a chance that the gradient might hit the cliff and then the norm explodes. So this is the example here. This is the exploding gradient. What we do is that we simply do not trust the norm that much. After all, what we trust from the stochastic gradient is the direction, not the how far we should move. So we can either clip the norm directly, as was proposed by the Razvan Pascanu in 2013, or we can clip the each of the elements separately. So either is fine. So it turned out that the gradient clipping is actually a very effective solution to addressing the exploding gradient. And then even in a very deep feed-forward network that is not the recurrent network, it turned out that the using gradient clipping is always beneficial. So I highly suggest you to use gradient clipping with arbitrary coefficients such as 1 or 5 whenever you can. It has a very nice connection to the trust region optimization method and so on. But all you need to know is that the norm of the stochastic gradient that you compute using a mini batch is not really the thing that you want to trust. You only want to trust the direction. Now that was a good news, but the bad news is the vanishing gradient is really, really difficult. And then this is true for a very, very deep feed-forward network as well. because there are two potential reasons behind the vanishing gradient. First one is that maybe there is nothing, there shouldn't be any kind of, let's say, dependencies. So that is, maybe changing the hidden state or the input and timestamp t should not influence what happens in the future. And then that may be because data is like that. If the data was created by Markovian process, just like in the n-gram language model, then there will be no dependencies or there shouldn't be any influence going beyond the n time steps, because how the data was created did not require any kind of such long-term dependencies. So this would be a fine reason to have the vanishing gradient, but even when there is that kind of long-term dependencies, if the parameters are not correctly configured, that is, if the largest eigenvalue of this U matrix is smaller than 1, or the 1 over the max of the hyperbolic tangent derivative, that is just a 1, then the gradient is going to vanish even if there is a longer term dependency to capture. And then we cannot really tell the difference between these two, because in order to know whether the data requires or the data exhibits this longer term dependency can only be told if we know how to train this kind of recurrent neural network really, really well. So it turned out that we cannot really distinguish between these two calls. So we're not going to look into this solution because this is not really used at all, but there were some attempts at trying to address this directly, but none of those attempts has worked out pretty well, not that well. So instead, we now are going to introduce a new concept called gating. And then this gating, or the ideas from these gated recurrent units, are very, very popular nowadays in trying to build even a defeat-forward network, such as the transformers and residual network. The idea of the residual connection, in fact, comes from this gated recurrent unit or the long short-term memory units. The idea behind the introduction of this gating is this kind of, let's say, realization that the problem of the vanishing gradient comes from the fact that the temporal derivative consists of the U matrix multiplied. And then this appears because the signal is propagated one step at a time only. So when we compute the HT plus 1, we only look at HT. When we look at the HT plus 2, we only look at HT plus 1. When we look at HT plus 3, we only look at the HT plus 2, and then so on and so on. And because of that, in the backward pass, we have to multiply the temporal gradient, or the gradient that is being backpropagated, with this transpose of this U matrix over and over. So then, of course, the natural question or the natural approach would be that what if we just introduce all these shortcut connections? If we introduce all these shortcut connections, then in the backward pass, there will be a path that are not actually going through all these intermediate steps, right? That makes sense. Oh, so just one quick thing, the question, can we consider using truncated backpropagation through time to handle vanishing gradient? No, that doesn't happen. That doesn't help. Truncated backpropagation, or the truncation, is in fact a perfect form of vanishing gradient, because it's going to simply say that, okay, there is no dependency or the influence that goes beyond this truncation horizon. So it's not a solution to the vanishing gradient. So the solution to vanishing gradient must involve this kind of shortcut connections that bypasses all these steps. So unlike before, where in order to compute the new hidden state, we only rely on the previous hidden state, right? So in order to compute HT plus 2, we only use HT plus 1. Now in this case, when we're trying to compute HT plus 2, we not only consider HT plus 1, but we're going to also consider HT as well, because we're going to introduce all these shortcut connections. But then introducing all these shortcut connections is very, very expensive, because every connection requires a new transition matrix, In other words, number of the parameters grows too quickly. So what we want is we want to have a adaptive shortcut connections. That is, we're going to introduce the shortcut connections, but only when they are necessary or when they are necessary to model the data better. And then we do that by this kind of so-called gating computation or the gating mechanism. So here's the previous hidden state. And then this is the candidate state of the new time step time t. What we do is we're going to compute the weighted sum of these two terms. So the previous hidden state and our candidate hidden state. And then how we weight them is going to be based on the neural network. So we're going to have an update gate that is computed by a neural network that looks at the same input, previous hidden state, and then outputs some value that is between 0 and 1. When it's close to 0, we're going to just copy the previous hidden state as it is because there's almost nothing to change. When it's close to 1, we're going to ignore the previous hidden state because we need to effectively reset the whole thing. And then this allows us to build all these shortcut connections in an adaptive way. And then we're going to also introduce a notion of the reset gate that can be used to prune unnecessary shortcuts, again, adaptively. Now, this is slightly less essential. It's pretty optional, although having a reset gate almost always helps up to a certain degree. Not too much though, not too much. So you don't have to worry too much about this, but it's good to know about this for the future thing. So, okay, so then we're going to skip this. So you should remember that what this gated recurrent unit does is just like what CPU does. What it does is that first, we're going to select the readable subset using this reset gate. So this is a reset gate. And then we're going to read that subset. So these registers correspond to memory in neural network. And then we're going to select the writable subset using the update gate. So we're not going to change the values of the entire memory, but we're going to only change a subset of that. And then we're going to update it by taking this weighted sum or the convex sum of the previous hidden state and the current hidden state. And then what this means is that this kind of gated recurrent unit, including long short-term memory unit as the gated recurrent units, are very much closer to the modern CPUs or the compute architectures than the vanilla or the naive transition-based model. So there are a couple of questions, right? So are we using information when we are resetting with the gates? And also what constitutes unnecessary shortcuts? So we are not losing information, or we lose the information that are not necessary for the future time steps, and how this network determines what information can be lost or not is entirely up to this neural network that is computing, that is computing the reset and update gates. So this is all learned. So these are all automatically determined which shortcut connection should be pruned, which information should be lost, or which information should be kept. That is the update gate, right? So all these things are done in that way. Okay, so that was the recurrent network, and then the lessons from this recurrent network, how the difficulties in training recurrent networks such as vanishing and exploding gradients, and how we address them by introducing all these shortcut connections turned out to be one of the fundamental ideas behind the success of the deep learning in recent years. So any kind of residual connections have been motivated from these gated recurrent units or the long short-term memory units. And also, when we're trying to initialize the weights so that they are not going to, the activations, normal of the activation is not going to explode, was also motivated from these recurrent neural networks. And also the gradient clipping is very, very useful. It's almost always used even when you train a feed-forward network that is not necessarily recurrent. So we are running out of time, so we gotta hurry up a bit. But you have the break. There is a buffer of the break before the QA with Yashua, so we're going to continue a bit further with how to build a machine translation system starting from this language model. So what we now know is how to compute the distribution over the sentences or the sequences, right? Using a recurrent neural network or any kind of neural network that can look into the indefinite history or the infinitely long history. All we need to do is we need to turn this around by making it into a conditional distribution where the probability of a sentence is conditioned on something else. And then this something else is going to be a sentence in another language. So, and then that is precisely what machine translation is, right? The problem of machine translation is to find the map between an input sentence or the source sentence. So let's not write it here. Is to map the source sentence into a target sentence that is going to be the translation of this source sentence. And it's a supervised learning problem, unlike the language model, because we are going to assume that we are given both source and target, and then we have many such pairs. And then the interesting thing is that we know already how to solve this problem because we learned about the language model and we learned about the text classification and we learned about how to get the continuous vector representation of the input. So first thing that you need to do is you need to build both the source and target vocabularies of the unique token. And it's very usual to use byte pair encoding or some kind of subword unit. You're going to learn more in the lab session, and then you already have heard about it yesterday as well. And then what we need to do is we transform each subword token into a corresponding one-hot vector. That is, just turn it into the integer index. And then the first component in this neural machine translation system is encoder. So given a sequence of the subword tokens in the source sentence, what we need to do is we need to turn them into a vectors or the continuous vector representations. So assume that we have the T prime long source sentence, then we're going to end up with H. There is a sequence of hidden states that corresponds to each word, H1 to HT plus 1, T prime. And then we can use any of the networks from our lecture 2 of the day 1, such as the recurrent neural network, convolutional network, or the self-attention. And then we're going to go into more detail about the self-attention soon, later today. But then one most important thing is that we do not want to get the one single vector representation of the full source sentence. We want to have a representation of the source sentence whose size changes as the length of the sentence changes. Because otherwise, the neural network encoder needs to learn to compress the any length sentence into a single fixed size vector, and then that turned out to be very, very difficult. And then we know that already because in 2014, I, together with my collaborators, we saw that when we use just a single vector to represent the full source sentence, the performance of the machine translation system is reasonable when the sentence of the source, length of the source sentence is limited. However, as the length of the source sentence grows, the performance dropped quite rapidly there. That's why we realized that, okay, the issue or the bottleneck is this, a single vector representation of the source sentence. Okay, there is one quick question. Is it correct to say that machine translation is a language model where the marginal probability is a different language? No, so it's not a marginal probability, it's just a conditional probability. So this is a conditional probability, right? So what we are trying to do is that in machine translation, we are trying to build a system so that the conditional probability of a target sentence is maximized given a source sentence if the sentence is a translation of the source sentence. So we're trying to maximize a low conditional probability of the correct translation given a source sentence. So that's what we are doing here. So this, and then this use of the multiple vectors or encoding the source sentence into a set of sentence representation vectors turned out to be the key concept for building a state-of-the-art neural machine translation system. So once we have this set of vectors, so there's H from H1 to HT prime from the encoder that represent the source sentence, we need to now have a decoder. And then decoder, we have already talked about decoder for 2 hours. And then we use the autoregressive language model with the infinite context because larger context is necessary for us to generate a very coherent and syntactically and semantically meaningful sentence. This is lecture 2. And then nothing really changes except that we do the language model, but conditioned on X. So every conditional probability of the next token is not going to be computed solely based on all the previous tokens in the source and target sentence, but also conditioned on the entire source sentence as well. And then how we do that is simply taking as input not only the previous hidden state, but also all the hidden vectors returned by the encoder that summarize the source sentence. So let's look at how we would build it. So we have this encoder. So this is the encoder. Encoder is going to compute the source sentence representations. And then we have the part of decoder that computes the target sentence representation. So notice that this is the up to yt minus 1, while the encoder looks at the entire source sentence. So we have the entire source sentence and what has been generated so far on the target side. And then this goes into some kind of neural net. So I'm going to call it some kind of neural net. This is a decoder. And then what this decoder needs to compute is to output a vector, a real value vector of the size that matches the size of the vocabulary. So there is the set of all possible next tokens. And then that goes into the softmax, and then that gives you the distribution over the next word in the target. And then of course the question is, how do we implement all these 3 boxes? The first, so we're going to look at the system from the 2015, that was actually the system by the Dima Bandanal, me, and Joshua Bengio. So if you have any questions, you can ask Joshua as well. We started with a bidirectional recurrent neural net on the encoder side. Now, unlike the autoregressive language model, because in the case of source sentence, because we are given the entire thing at once, we can now use the bidirectional recurrent neural network. So we have a forward recurrent network, and then we have a reverse recurrent network. And for each token, we're going to concatenate the hidden state from these forward and reverse recurrent neural networks, and then say that, okay, this is a representation of the corresponding word within this context. So what is the meaning of this word within this sentence? This is really important, right? Because each word can have multiple meanings. And then once we see that word in this context of a sentence or a paragraph, we can now precisely identify what the meaning of this word is. Like traditional or the typical example is a word bank. Bank can mean financial institute, but also bank can be used to indicate the river bank. And those two are 2 different meanings. If you are given only a bank, we cannot tell. However, if bank is used within a context, and we can tell exactly which of these 2 senses the Bank was referring to. And then that disambiguation is done by this bidirectional recurrent network. Now, in the case of the target side, in 2015, we used a unidirectional recurrent network, just like how we learned how to build a recurrent language model, recurrent neural net language model earlier in this lecture. So we're going to simply read one word at a time, and then whatever has been outputted from this recurrent neural net, after reading the T-1 tokens, is going to be the representation from the target sentence encoder. So that's going to decode the recurrent neural network. And this network summarizes what has been translated so far. And then now we actually, in 2015, we introduced the attention or the differentiable or soft attention mechanism. That is, which part of the source sentence. So we have the representation from the source sentences here. And then we have the representation from the target prefix or what has been translated so far. And then the idea was to use the attention mechanism to try to score each and every one of these hidden states from the encoder or the source side against this, what has been translated so far, the representation of that. We score each one of them. And then what we do is we're going to compute the weighted sum of all these encoders hidden state into the time-dependent context vector CT. We're going to go, let me see. Will the Joshua Benjo QA be on Zoom? I actually don't know. I think the tutors probably know. So it'll be nice if the tutors could share the link for the Joshua Benjo's QA on the campus wire so that the students at both Ghana and Rwanda, as well as we from New York City, can attend the Joshua's QA. So let me see. I thought I actually, okay. So then we compute this time-dependent context vector. So this is going to be a one vector that summarizes a source sentence with the entire source sentence with respect to what has been translated so far, with some different weights given to different hidden states. And then this results in the time-dependent source context vector CT, which is now going to be used in order to compute this final distribution over the next target word. So let's look at the overall picture here. So we started with the source sentence, and then we now have the what has been translated so far. We have the encoder, we have the decoder, and then within it, we have this attention mechanism. This attention mechanism is going to give us a time-dependent context vector. And then we're going to use the hidden state from, so this is the what has been translated so far. And then based on this, we're going to have some deep neural networks. So it can be any kind of directed acyclic graph that's going to give us ultimately the distribution or the conditional distribution over the all possible next target word, given what has been translated so far and the source sentence. This is what it does. So let me try to answer one question quickly. Can we say that the attention mechanism, there is no need for the bidirectional? No, for the attention mechanism, you really need the bidirectional recurrent neural network because source sentence representation needs to know in which context each of the word happens. So if I wanted to know the meaning of this second word, I need to know what it means within this context of the source sentence. And the attention mechanism relies heavily on knowing the precise meaning of each of the words. So it is important to use a bidirectional recurrent neural network. However, we're going to talk about it after Joshua Benjo's QA self-attention mechanism much more carefully. And then there, we're going to know that the bidirectional recurrent neural net may not be necessary. It doesn't have to be a recurrent network. It can be some other mechanism. So conceptually, it consists of 3 stages. First, we encode the source sentence. And second, we attend to the relevant tokens. And then lastly, we decode the next target word. And then we go back and forth between the step 2 and step 3 over and over until we decode out the end of sequence token, the special token that indicates that the sequence or the sentence has terminated, as you saw yesterday already at our lab sessions, right? So it turned out this attention mechanism is extremely powerful in that even when the sentence length grows, the translation quality measured by the blue score does not drop. And the blue score is our way to automatically measure the translation quality by comparing what has been generated against a human translation that is a reference translation. And it measures the geometric average of the n-gram precisions weighted by so-called gravity penalty that tells us how long a translation is. Unfortunately, I don't have time to go through the blue score carefully. I believe in one of the lab sessions later today is going to talk about blue score and how to compute this, because that is going to be the, let's say, one of the important metrics that we use to tell which machine translation system is better when human evaluation is not available. So this is some of the examples of the source and target sentences when the attention mechanism is used and when the entire source sentence was compressed into a single vector. You can see that initially the model can translate reasonably well, even when attention mechanism was not used, but it easily breaks down afterward, right? I believe many of you already know how to speak French, so you probably can tell better this, because I don't really speak French. However, with the attention mechanism, this kind of deterioration in the latter part of the translation does not happen. And this kind of attention mechanism is really nice because it allows us to do some kind of visualization on what is happening. And later today in the second lab session, we're going to look at how this kind of visualization works and then what kind of intuition we can get from this kind of visualization. And then just one thing to emphasize for me is that these visualizations happened automatically. We did not give any indication on which words corresponds to which other words in different languages. So, and then now this neural machine translation system is used everywhere, from the Google Translate all the way to even the European Patent Office. And then more recently, people started to build a neural machine translation system for languages in Africa as well, with the advances in the low resource machine translation. Unfortunately, I don't have time to go into the low resource machine translation, but if you search for low resource or the unsupervised machine translation, you're going to find many recent papers that talk about how to build a machine translation system with a minimal amount of data. So in practice, of course, this is the old version. Oh no, I thought I updated on the Google and Google Drive, but it didn't. So now, if you want to build the actual machine translation system, you don't want to build everything from scratch. So you're going to look at how to build them from scratch in the lab session, but you don't have to do that yourself if you want to build a commercial grade machine translation system. You use these excellent open source packages, such as the Nematus or the FairSig, or if you want to go for a very fast machine translation system, you use something called, something called Marian NMT. This is the fastest tool that is available out there. So I highly suggest you check that out. And then of course, we're going to talk about the transformers a bit in the second part of the lecture, second lecture, but that has become the de facto standard. However, the transformers tend to be really, really large. So it's often in practice, the mix of the transformers, the self-attention and the recurrent network. Convolutional networks, unfortunately, are not really being used that often these days anymore because the recurrentness and the transformers tend to work better than that. So that actually concludes the first lecture of today. We are going to have the QA session with the Joshua Bengio, and then we're going to continue with the attention mechanism at, let me see, 9:45 New York time, which is going to be 3:45 p.m. in Kigali, and that is 1:45 in Accra. So I'm going to post the Zoom link again on the campus wire near that time. But until then, enjoy the QA with Yashua Benjo and enjoy your break. And if you have any questions, post the questions on the campus wire. I'm going to try to answer as often as I can. All right, class dismissed. Thank you.